So, what we studied in the last class is the OSI reference model. The model having 7 layers. From the bottom, the physical layer, the data link layer, which is divided into 2 sub layers, the upper one being the logical link control and the lower one having the being the MAC layer. And above the data link layer, you have the network layer, who does the function of routing the packets or the data from one host to the other host. Then above it you have a layer which is responsible for the process to process communication, that is the transport layer, followed by the session layer, who starts the session and terminates the session after the communication is over, and then you have the presentation layer, and finally the user layer, what we call the application layer. At the sender side, how the data is being transmitted or generated by the user and how it goes till the physical layer, and in between every layer adds its own control information as a header, and finally it becomes a frame in the data link layer, and the data link layer pushes the data into the physical layer and ultimately to the channel, the cable, maybe a wired. We are considering for the timing the wired cable or the wired media. So, it is entered into or released to the channel and then it is transmitted to the receiver. That is what we covered in the last class. Now, if I say this is the sender side and here is the physical layer, the physical layer releases the data into the channel, or here is your transmission cable, the wire you can say. Now, the 1 or the 0 that comes from the sender side reaches to the receiver side now. So, as we had seen in the previous class, there are 2 data chunks, one is D1 and another is D2, and D1 was encapsulated in a frame having different headers in different layers, and similarly D2 was encapsulated in another frame and encapsulated with other header fields. Now, let us say this frame 1 arrives to the receiver containing the data D1. If this is the data D1, this frame contains a trailer information that was encapsulated by the DLL of the sender, and header information that was by the DLL layer. Then there was another header field that was encapsulated by the MAC layer, the network layer. Then another header that was encapsulated by the transport layer, and any other header field that may be added by the other layers while coming from the sender side. Now, when it comes to the receiver, it first goes to the physical layer of the receiver. What the physical layer does, it receives the series of zeros and ones that has been transmitted by the sender, and after receiving it does some kind of error checking. You know, there are different kinds of error checking methods are there, right? Just the preliminary error checking is being done to check whether the format of the data that was being transmitted has come to the receiver or not. Now, after this, what the file layer does, it sends the data to its upper layer, that is the DLL of the receiver side. So, when the DLL comes to the receiver side, because the sender DLL has sent a header as well as a trailer information to its peer layer or the peer DLL, this header and the trailer is understood by the corresponding DLL of the receiver. So, what it does, it decapsulates the header and the trailer that was being encapsulated by the corresponding sender, right. So, that was whatever was encapsulated here is being now decapsulated at the receiver side. After doing this, the DLL now sends the data to its upper layer, that is the network layer. Network layer finds the data chunk which has been encapsulated by another header field which was encapsulated by the sender network layer. So, what it does, it understands this encapsulation being a peer layer of the sender. What it does, it decapsulates it now. Your D1 or the data remains intact, no one is disturbing the data that was being transmitted. So, what they do? They only encapsulate their header information and decapsulates the header information, that is all. And with this header information, they get all the kind of control signals, all the kind of informations that are being sent by their peer sender. Now, once the network layer header is decapsulated, it goes to the next upper layer, that is your transport layer. And this transport layer, what it does? It decapsulates its corresponding header. So, what is left out is now only the data D1. So, the data that has been traveled all the way from the sender side, encapsulated with different header fields, is now being traveled all the way in the receiver side, and all the header informations were decapsulated, and you get the original data D1 whatever had come from the corresponding peer layer. Now, it goes to the other layers, they do their job, the session and the presentation layer, and finally, it reaches to the application layer as an intact data D1. And same thing happens for the next frame D2. This also travels all the way from the file layer to the application layer, and now it is added with the previous data D1 and D2, and finally, you get the actual data that was being generated by the sender in the application layer as D. So, your data that is transmitted from the sender to the receiver has been processed by every layer in different way, but the content or the data remains as it is, the way it was generated and the way it is received. There is no difference between these two. That is the efficient communication. If this D and this D does not match, that means there is somewhere problem in any of the layers who has not done their job perfectly or efficiently, for which you are not getting the original data that was supposed to be received by the receiver. That is what is your data transmission and the different layers, the job of the different layers in the OSI model. Coming to the next kind of reference model, as we discussed, there is another reference model, the name is TCPIP. This is a very simple model having very less number of layers. The reason behind is what they believe only the layer that does a specific function and whose protocol is defined properly has to be mentioned in the reference model. So, this model has got less number of layers, you can say only 4 layers are present in the TCPIP model, and those layers are, the first one being the host to network layer. The host to network layer. This layer actually we assume that this is a combination of your file layer and the DLL in case of your OSI. It maps the same, it does the same job what the physical layer and the data link layer of the OSI reference model, what they do, the same job is being done by the single layer host to network layer in the TCPIP protocol or the reference model. Now, above this we have a layer called the network layer, but TCPIP name it as the IP layer. The network layer that is being named in the OSI reference model is now named as the IP layer in the TCPIP, the internet protocol layer. The job is same. In the OSI model, the network layer does the job of routing. Here also the IP does the same routing, but because it is a standardized protocol, we say this is an IP layer. Then above this network layer or the IP layer, the reference model has got the same transport layer as in case of your OSI reference model, and the job of this transport layer is also same. It supports the process to process communication, or you can say the actual end to end communication. And above this, as usual, you have the application layer. Now, there exists some technical difference between the TCPIP reference model and the OSI reference model in terms of 2 layers. One is the transport layer and another is the network layer. In TCP, in the OSI reference model, if this is OSI reference model and this is the TCP/IP, what the OSI model does for the transport layer, this uses only one protocol, and the kind of service that is being supported by this protocol is a connection oriented protocol. The service is connection oriented. But while coming to the TCP/IP reference model, the same transport layer has got two protocols. One is TCP, another is UDP. One being the TCP being the connection oriented and UDP being the connection less. UDP is a connection less protocol for TCP/IP reference model, and TCP is a connection oriented transport layer protocol in case of TCP/IP reference model. So, definitely the reliability of TCP will be more or UDP will be more. TCP is more reliable in terms of communication or the transport layer functionalities. Now, coming to the network layer. OSI model it supports two kinds of services. One is connection less, another is connection oriented. OSI reference model supports two kinds of services in the network layer, one being the connection less and another being the connection oriented. So, you have two kinds of routing protocols or networking protocols in OSI reference model. One is the circuit switching and another is the packet switching, right. So, packet switching being the connection less and circuit switching being the connection oriented protocol for network layer of OSI reference model. While coming to the TCP/IP, it is just the reverse. It only supports a connection less protocol. It supports only connection less protocol, or what we say IP or internet protocol is a connection less protocol. So, no connection oriented service is provided by TCP/IP in the network layer, whereas the network layer of OSI reference model supports both the connection less and connection oriented. And just reverse in case of a transport layer, where the OSI model supports only connection oriented protocol, the TCP/IP reference model supports both the connection oriented as well as connection less protocols. So, you have TCP and UDP. So, this is what is the difference between your two reference models. Those are very popular these days, the OSI reference model and the TCP/IP reference model. So, now we have studied enough about this computer networks basics, like how they do, why you need it, how the layers are being or the computer network has started, how the reference models are designed, why you need a protocol and all those things. Now, let us say you designed a network, with all those hardware requirements that you have seen and all the software requirements, the protocol designing, everything. Now, how you say that the network that you have designed it supports the efficient communication, or it is the standardized one? There must be some measuring parameter. You must say that this is working fine, means you have measured some parameter, right. So, when you say a network is a better network, even if you are using different networks, communication networks or the service providers, you say BSNL is good or bad, Airtel is good or bad, something. Why? You have experienced something. What you experienced? Maybe time may be a factor, maybe some kind of quality of service of some measuring parameters that you have experienced, for which you say this network is good, that network is bad, right. Similarly, in any network, when it is designed, it has to be standardized in terms of some measuring parameters. And what is the primary goal of any communication is transferring the data from one end to the other end. So, when it is transferring the data, the first thing you remember, what is the throughput of the network? Throughput means how much data in a specific time it is able to transmit, and another is how much time does it take to transmit this much amount of data. Definitely delay is one parameter or one of the prime goal for any communication network to say, yes, I am having the right kind of communication channel or not. So, what we say, to study this, we usually say this as the network performance. Network performance. If the network performance is good, you say this is an acceptable network. It is not, then you do not accept it. To measure the performance, we have usually two dimensions. We measure the performance of any network with two dimensions. One parameter is a bandwidth and another is latency. The latency is also termed as delay, and bandwidth leads to throughput. We will see what exactly is the difference between a bandwidth and a throughput, right. Now, what is bandwidth? You must have studied till now. What is bandwidth? The range of frequency that can be accommodated. Let us say if you are saying a telephone line, the telephone line can support, let us say, some frequency of 30 hertz or 300 hertz to 3300 hertz, right. Usually mentioned in that way, it is a range, we say in terms of a range. So, what is the bandwidth of this? Bandwidth is 3000, right. When you talk about any container, you can say, or a channel that handles some signal, maybe audio signal or any other signal. When it comes to the transmission or communication channel, in that case, when bandwidth comes into picture, we say how many number of bits or how much bits it can accommodate or maximum it can transmit in any unit time. So, if you define bandwidth, we say bandwidth is nothing but the number of bits that is being transmitted over the network per unit time, let us say. So, bandwidth is the number of bits transmitted over the network per unit time. If I have a cable, like this or a channel, and the capacity of the channel is 1 MB. What do you mean by this? The channel capacity is 1 MB, meaning total 1 MB data it can hold at any point of time, right. Maximum 1 MB of data can be sent into the channel and it can transmit, that is expected. The capacity of this hall is 120, meaning maximum 120 people can be accommodated in this hall, that is the capacity of this hall. So, the capacity of a channel is actually the bandwidth, how much data or how much bits of data it can transmit at any point of time. So, if I say the bandwidth of any channel is 5 Mbps, what is the capacity of this? What is the capacity of this channel? It can hold that much of data at any point of time. If I say it can transmit 5 MB of data in 5 seconds, if I say a channel can transmit 5 MB of data in 5 seconds, what is the bandwidth of the channel? It is 1 MB, right. That means the expected amount of data that could be held in a channel is actually the or it can transmit. Hold means it can transmit, that is the capacity, that is the bandwidth of a channel. The another parameter as we discussed is the latency. Latency means what? Let us say there is a channel here, a node or an user A is connected to the channel and it wants to transmit the data. This is a host or a computer. What it will do? The first step that it will do is it will generate the data. Agree? It will generate the data. Then what it will do? It will release the data into the channel. It will take some time. Then the data will be transmitted over the channel to reach at the destination. If destination is B, it will take some time from here to here, right. So, if A takes 2 milliseconds of data to generate and 10 milliseconds to transmit, so what is the total delay for transmission of the actual data? Is 12 milliseconds, right. So, if a node is having 1 KB of data and another node is having 1 MB of data, If A is having 1 KB of data and B is having 1 MB of data, then who will take more time to release the data to the channel? A or B? It is obviously B, considering both A and B are performing at the same speed, right. Let us say both are having 1 KB of data, A and B. One is a slower one, another is a faster one. Who will take more time? Definitely the slower one, because it is generating in a slow speed than the faster one. So, that means the generating of the data or sending the data to the channel is not a channel dependent parameter, rather it is a function of the computer, I mean the node who is generating the data, as well as the capacity of the network or the bandwidth of the network. If the bandwidth of the network is not high, it cannot hold the data. Even if the node is a faster node, it can generate the data, but if the channel is not able to hold it, there is no point. The data will be dropped and it will lose, right. So, to consider this, the delay or the latency, now I will term it as a delay because it is very frequently called as delay, transmission delay. It could be again of two types. One is one-way transmission from sender to the receiver, that is possible. We say it is a one-way transmission. Let us say the sender wants, or the requirement of the scenario is that it should go back to the receiver and again it will come back to the sender. We say that is a round trip delay, right, or usually termed as RTT, round trip time. So, either the delay could be one way delay or it could be a round trip time delay or the RTT. So, when we say this delay, now delay has been considered, it consists of three major components. First is the speed of the light propagation delay, actually it is the propagation delay. Why say that is speed of the light? You know it, the transmission usually we say the speed of the light is the faster transmission, so we compare with that. And how much is this? Speed of the light is, it is 3 into 10 to the power 8 meter per second if it in case of vacuum, right. It is 2.3 into 10 to the power 8 if it is in case of a cable, and it is 2.0 only 10 to the power 8 meter per second if it is in case of a fiber. Now, you realize why the fiber optics communication is faster than any other communication. This is the fastest one, the fiber optics communication. This is a wired communication and this is basically for your wireless communication. So, why it takes less time in fiber optics, why it takes little bit more time in a cable, but when it comes to a wireless one, it takes some more time, the propagation delay, right. Then another is this is the propagation delay. The second component is time to transmit the unit data. This is the actual transmission time, transmission of unit data, transmission of unit data. This is what I say is a function of the bandwidth and the packet size. As we discussed, a node having high chunk of data will take more time than a node having small chunk of data. The reason behind is more data, more time to release into the network. And even if you take a different node with different speed, then definitely the faster one will take less time and the slower one will take the more time for transmitting into the channel. Then the third component is the queuing delay. The queuing delay. The queuing delay usually occurs even within one computer or one node. Let us say 5 processes, let us say there is a host here and 5 processes P1 to P5, they are generating data. So, P1 has got a data D1, D2 this way. Now, let us say all this data D1 and data D2 are being transmitted and in the meantime the processor P5 generates a data D5. When it generates D5, the D5 has to wait for some time to get the channel to whom it can release the data. That means the data that is being generated by P5 will be in queue, so that it gets the channel and releases the data to the channel. So, if you see the total latency is equal to the propagation delay plus the transmission delay plus the queuing delay. And what is the propagation delay? The propagation delay can be defined as, it is the distance of what? Distance of the channel that it has, or the distance between the sender and the receiver divided by the speed of light. That is what is your distance of the propagation delay. And what is the transmission delay? Transmission delay is nothing but your size of the packet divided by the bandwidth, and another is the queuing delay. This is like if you have a channel, a very simple case, your sender is A, your receiver is B, and the channel is a cable. Now, A is generating a packet P1 or D1, and P1 is in a queuing delay to be solved and to reach the channel or to get the channel to send the data, that is your queuing delay. Once it gets the channel, it now starts releasing the packet into the channel or generating the packet into the channel. That is what is your transmission, transmission delay. This is the transmission delay, and now this will be transmitted or propagated over the channel, and this is called your propagation delay. Sometimes queuing delay may be 0. The reason is that it is an idle computer. So, whenever it generates the data, it sends it, unless otherwise it is mentioned that it has to wait, or the node is in a queue or it is waiting for some time to get the channel, the queuing delay is usually considered to be 0. We assume that as soon as the computer is ready, it gets the channel to transmit the data. But there will be definitely some transmission delay, and this transmission delay will depend on your size of the packet and the bandwidth of the channel. Then your propagation delay, where you are propagating, in the vacuum or in the cable or in the fiber optics. So, this is how your total propagation delay is being, total latency is being considered. Now, which one you will prefer, a high latency or a low latency? And definitely a network having very less latency will be considered as a faster network than the other one. So, whenever a packet or a node is ready to transmit, the designer makes sure that there is no queuing delay and there is least transmission delay. So, if you use a channel with a better bandwidth, definitely the transmission delay will be very less, and make the packet size so small, not exactly so small, it is optimized, so that it takes less time to be transmitted to the channel. And then propagation delay is not usually in the hand of the user or the designer. It depends on the cable, the different noise, there will be some attenuation, some traffic. So, again they work on the channel side to reduce the propagation delay. So, 3 parameters of delay combines to give you the total latency of communication. And another term that we studied is the throughput, which usually comes from the term bandwidth. So, what is throughput? As we discussed, there is a term called bandwidth, means it is the actual capacity of a channel. How much data or bits of data it can hold at any point of time, or it can transmit, that is what is your bandwidth. But usually it is seen that the total bandwidth is hardly used by any transmission. So, let us say the bandwidth is 10 Mbps, but a user who is using this channel may actually get 2 Mbps of data. Otherwise, You must be seeing you are having a channel or connectivity of 1 Mbps, but the actual data transmission is very less, right? Why that happens? Why that scenario comes? You have a bigger channel bandwidth, you are using 1 Gbps bandwidth, but when you get the data when transmitting you get hardly 1 Mbps, that is also enough. The reason behind it is that you do not get the whole bandwidth for your transmission. So, the measured performance or you can say the measured performance of your transmission is called the throughput, and bandwidth is the available capacity, but you never get the whole of the available capacity for your transmission. So, available capacity is bandwidth, and the measured performance or the actual transmission, you can say actual transmission is the throughput. That means you can say that there are two nodes N1 and N2, they have a connectivity of bandwidth 10 Mbps, but when they do the transmission they get only 2 Mbps to transmit, and we say this is the throughput of the transmission. That is what is actually you measure a network performance, you have something available to you, but the real transmission gives you some other result. You have some different parameters which you can control, you have some parameters which you cannot control in transmission. So, combining all this you have a network performance measurement, and with this if you get a better result you say that I have a standardized, I have designed a standard network who can have a faster communication with least highest throughput. That is what is your measuring performance or the network performance, right.